Hi all, my name is Arun Zakaria and today I will be presenting a work on the context-aware visual redaction pipeline. Before diving into the technical details, let's have a quick look at a plan for this presentation. We will begin with an introduction to define the privacy risks and compliance challenges associated with large-scale training data. Next, we will look at previous work in image embedding and discuss the limitations when applied to automated large-scale redaction. From there, we will detail our proposed framework, looking at how we integrate object detection with vision language models. Finally, we will show a brief demonstration of the end-to-end system processing of assets in real time. To give some background, large-scale visual datasets used for training modern machine learning models frequently contain proprietary logos, protected trademarks, and personally identifiable information, or PII. When leading diffusion models are trained on this data, they run a significant risk of memorizing and subsequently reproducing these protected visual assets during downstream generation. This creates severe compliance and legal challenges. A common approach is to apply standard filtering methods after image generation. However, post-generation filtering does not clean the underlying training data itself. To prevent concept leakage entirely, the pre-trained data needs to be cleaned. To address this, we propose a framework that automates high-fidelity visual redaction across massive collections of images and video sequences. Crucially, by replacing the sensitive regions with contextually relevant alternatives rather than blank masks, our pipeline preserves the quality and semantic utility of the dataset for the downstream training. Before diving into our architecture, let's look at the existing approaches to image editing and erasure and why do they fall short for this specific task. First, classical mathematical inpainting techniques such as Navier-Stokes or fast-marching methods operate by propagating pixel colors from neighboring boundaries inwards. While computationally efficient, they lack any semantic understanding of the scene. Consequently, when applied over large target regions, they produce severe blurring and highly noticeable structural artifacts. Second, texture patch replication systems, like say for example patch match, fill targeted regions by copying and stitching matching texture patches across these unmasked spaces. While this handles basic textures well, these algorithms fail to maintain perspective or structural continuity in some of the complex architectural or environmental scenes. More recently, diffusion-based inpainting models have shown the ability to produce highly realistic textures. However, their success depends entirely on descriptive text prompts to correctly match the specific background of the surrounding scene. Without a human manually writing these prompts, standard inpainting models suffer from contextual misalignment, meaning that they introduce arbitrary or irrelevant objects into the masked ones. This alters the original data distribution and degrades the dataset's utility for model training. To solve the prompt bottleneck and eliminate human-in-the-loop dependencies, we developed an automated modular pipeline. I will now walk you through the core components as seen in the architecture diagram. The first is the protected content detector. This uses an object detection network, which for our demo is a fine-tuned Euler model, to localize targeted logos as sensitive identifiers, outputting precise bounding box coordinates. Next, the dynamic prompt generator automates the text prompting step. It takes a spatial graph of the bounding box area and feeds it directly into a vision language model. During VLM contextual interrogation, the VLM acts as a zero-shot scene analyzer. It evaluates the immediate background environment of the cropped region and generates descriptive text to capture the local context. For instance, instead of seeing a logo, it identifies a logo sitting or placed on a metallic surface. Finally, the guided inpainting engine takes over. It combines these three distinct inputs: the original image, a binary pixel mask derived from bounding boxes, and the dynamically generated text prompt from the VLM. These inputs condition the latent space diffusion model inpainting process, ensuring that the synthesized pixels blend seamlessly into the original background environment. To demonstrate the system in action, let's observe a direct execution of the pipeline. We input an image containing a prominent logo. The system automatically localizes the assets and creates a localized graph and prompts the VLM. The VLM is able to identify the background context, and you can also see the sanitized output. And as you can see, the logo has been completely removed. Rather than leaving a blurry patch or an empty black box, the guided inpainting engine has filled in the region with semantically consistent content. The pipeline scales natively to video sequences. Let's see it in action on this video. And you can see in the output, the logo has been eliminated entirely without introducing any kind of temporal filtering or any background distortion. So to conclude, our framework successfully couples object detection with vision language models to achieve scalable, high-fidelity data sanitization. The source code and project details are available publicly on GitHub, and I thank you for your time.